Hi, guys. So, this will be your mass and weight lecture um, for your mass and weight handout that you're going to put into your notebook as number 28. So, to start off with, we have your general definition of mass and weight. So, on your handout, I would like you to circle or highlight the areas that I've boxed and write definition to the side. So, mass, the definition of mass is the quantity of matter in an object. So, it's what the parts that make up the object is what mass is. Weight is the force on the object due to gravity. So, weight only exists when there is gravity on a mass. Mass exists whether or not there is gravity. So, on your handout, go ahead and take a minute and mark the two definitions, as well as anything in particular that I just described to you onto the side here. And then it says it is also the measure of inertia or sluggishness that an object exists in response to any effort made to start it, stop it, or change a state of motion in any way. This is Newton's first law. So on your notes, you're going to add Newton's first law, just as a reminder that that is what it's talking about. So when we measure inertia, we typically measure the mass when we're talking about motion in a straight line. We have a later definition of inertia that's a little bit different, but we'll be getting into that later on. All right, in the next slide here, we have mass, a measure of inertia of a material object. So that would be a definition, a key phrase. It is independent of gravity. So the gravity doesn't have to exist for it to exist. The unit of measurement, the SI unit of measurement, is the kilogram. So when we are performing calculations or looking at any kind of numbers in physics, we're looking for the SI unit. Okay, so that's what we're looking for, is the SI unit, and for mass, that unit is kilogram. The British unit is actually called the slug, which is a term that we really don't use. We use pound to refer to the weight of an object. And interchangeably, this is often used to describe the mass of an object as well. But technically, the mass of an object in British units is the slug. And that's a unit that we are actually using in the US. So kilogram is the mass unit for SI units, and Newton is the weight unit. But in the US, we use pound for weight as well. And so the corresponding, as I said, the corresponding unit is the slug. So Newton and kilogram, and slug and pound. Okay, so let me go ahead and explain this here. We are solving, let's see if I can just erase some of this little stuff here. Okay. If the mass of an object is halved, the weight of the object what? So this is just picking somewhat arbitrary values here. I am using 10 meters per second squared for gravity. And then I'm arbitrarily picking 20 kilograms for mass, just as an example. And 20 times 10 would be 200. So newtons would be 200 newtons of weight. Now, if it says if the mass is halved, what happens to the weight? So we are assuming that the gravity is the same. Okay, so this is going to be equal. Mass halved would be 10 kilograms. Gravity would stay 10. Okay. And then that would give us a value of 10 times 10 is 100. 100 newtons would be the weight. So if the mass of an object is halved, 20 becomes 10. The weight of the object is also halved. Okay, so the correct answer would be A. So on your notes handout, I should see A marked as correct answer, and I should see this right here showing the working out of that problem. So you should have weight equals mass times gravity. You should have 200 newtons equals 20 kilograms times 10 meters per second squared. And then you should have the drop down where we do half of mass, gravity is the same, and we calculate 100 newtons. All right, slide 4. So when mass and weight in everyday conversation are interchangeable, however, they are different. Mass is what we refer to as more fundamental. Another way of saying fundamental is basic. So mass can actually exist without weight, but weight cannot exist without mass. And to show you a mathematical example of that, weight equals mass times gravity. If I have a mass of 100 kilograms, but I have 0 gravity, then I have 0 weight. If I have a lot of gravity, but no mass, I also have no weight. So it is possible to have mass without weight, but it is not possible to have weight without mass. So if there's no mass, it doesn't matter how much gravity there is, you don't have any weight. But mass can exist by itself without weight, because weight is just the force of gravity on a mass. So without mass, it doesn't exist. And that's what you should have on your slides. This is what you should have labeled, and you should have this example here. I would also suggest that you write on the side here my explanation that mass exists without weight, but weight does not exist without mass. And that's what this calculation up here is showing you. Mass versus weight. So on the moon and Earth, the weight of an object on the moon is less than on the Earth because gravity is less on the moon. But the mass of the object is the same in both locations. So if you were to take any object from Earth, take it to the moon, all the same pieces of that object would be there, meaning that the mass was the same, but the weight would change because the force of gravity changes when you are on the moon versus on Earth. And you'll explore that tomorrow in your lab. You'll be doing a gizmo lab, and you change the gravity to the different planets, and you can see the weight of the object change, which is pretty interesting. All right, slide number 5. Weight continued. 1 kilogram weighs 10 newtons, or 9.8 newtons to be precise. The relationship between kilograms and pounds: 1 kilogram equals 2.2 pounds equals 10 newtons at Earth's surface. 1 pound equals 4.45 newtons. Now, it's a little bit of a false equivalency because if you remember from the previous slide, the kilogram is comparable to the slug, and the newton is comparable to pounds. So even though you can say if we are on Earth, then 1 kilogram equals 2.2 pounds, technically those are different units. So newtons and pounds are comparable because they are both weight, but kilograms to pounds isn't a direct relationship. It's actually a calculation. So this is showing here, if I have 100 pounds, there's 1 pound per 4.5 newtons. So 100 pounds would be 445 newtons. Just to give you an idea, so if you are using newtons, it's going to be a lot bigger than you think it is. So someone weighing 100 pounds would be 445 newtons. If I'm converting 100 pounds into kilograms, it would be 1 kilogram is equal to 2.2 pounds on our surface, and that gives us 44.5 kilograms. All right, so the equation to convert between mass and weight is weight equals mass times gravity. And this is just a specific version of Newton's second law, which is force equals mass times acceleration. Weight is a type of force, mass and gravity is a type of acceleration. So it's essentially the same equation here. Force equals mass times acceleration. It's just a specific type of force and a specific type of acceleration are used. And we'll get into that more later. So let's proceed here. Okay, so the sixth slide on the handout we will actually talk about later. It kind of ties in actually to the next lecture, so you can just leave that one blank. So here's what the handout looks like. So this slide right here, you can leave blank, but there should be annotations on the other 5 slides, as I've just demonstrated to you in this video. You're also going to answer the questions at the end of the Go Formative. So for the handout, I expect you to have annotated the 5 slides that I showed you in the video. And then on Go Formative, I want you to answer the questions that are below. So questions 6 and below are the ones that I want you to actually answer on Go Formative. You do not have to annotate the slides in Go Formative. So your copy just shows blank slides. I want you to annotate on your paper version. So you don't have to go through where it says show your work. You don't have to do that. I just want you to put all of that onto your paper handout. You will be answering questions 6 through 11 on the Go Formative.